Okay, what we have seen in the last lectures is that if the most general N=1 supersymmetric the grande demostrazione N=1 supersymmetric H0 can be written in this form. This curve this thing of tau over time. So, just keep. Therefore, the most general, giving a set of chiral fields, phi A are chiral superfields, in a given representation, in some representation. Okay. And V is a vector superfield. Okay. We see that this is the most general Lagrange, which is given in terms of real function. And two holomorphic functions. And this is what is called prepotential. This is called superpotential. This is called the
So in the first integral, you mean for day to 4, day to 2?
The 4 theta means V2 theta.
Yes, right.
V2 theta bar. And here plus and check. Okay, about these two types of terms, these are chiral terms, chiral couples, and these are non-chiral. Okay, and everything is given in terms of this thing. This was the most n equal to 1, and we said everything is given in terms of V, which contains a vector, and a vector which is the gauge field, and Fermions, which is called gaugino, an auxiliary field V. And all the phi A are contain one scalar, one fermion, and one what they call F term. Okay, these are auxiliary fields that enter in the equation without derivatives. This means this is the equation of motion of these are algebraic. So these are not divisible. Okay, then for n equal 2. You see that n equal 2, what we do is we combine a vector plus a chiral. Okay, in the joint. And this we can call vector of n equal to 2. And we combine chiral plus anti-chiral, or let's say chiral representation R. If a chiral representation R bar, and this is what we call high Fermion. Okay? Then the theory is just a special case of n equal 1. And it's a special case in which everything is given in terms of a single prepotential. Okay? Which depend on the on your fields. Okay, here maybe I should say something. Okay, when we will go to n equal 2, we will say more precisely. But okay, the important point is that the n equal 2 is a special case of n equal to 1. For example, pure, let's say pure n equal 2 corresponds to the choice where k is equal to k is roughly derivative of f respect to phi and phi bar, and tau is tau phi, and that's w is equal to 6. And tau is the square of f different. Pure n equal 2 means a theory that contains just this, a vector plus one chiral. If I call this chiral phi, this corresponds to a special case in which this scalar function is just giving us one derivative of the prepotential. This W is 0, and this tau is the second derivative. This is the most general pure n equal to 2 theory. In general, if you have a more complicated theory, you will have a prepotential which depends on the various kinds.
What does pure mean?
Pure means that it contains just a vector, no hypers. Finally, we have n equal to 4, and in this case, we have vector plus 3 chiral. Everything is in that joint. This is what we call vector of n equal to 4, and the action is completely fixed. In this case, k is equal to phi bar. Tau is constant, and W is phi bar. So 3 chirals in the okay. Then okay, this we done, and then what we did was we considered the case n equal to 1, what is called super QCD, which is n equal to 1 is 1 gauge 0 plus a chiral field in the fundamental and a chiral field in the anti-fundamental. Okay. You see, this is a sort of generalization of QCD. In QCD, you have just a vector boson in the SUN, okay? And you can imagine this like the quartz. The quartz performing the fundamental of SU3, okay? So this is like a quartz, and this is like the anti-quartz. Super QCD.
Sorry.
Oh, of course, this is supersymmetric. Therefore, you have also, apart from quarks, you will have quarks, scalar particles which are the supersymmetric partner.
So, is it an off-shell? This superspace in for n equal 4 are off-shell or on-shell?
There's no superspace in n equal 4. I always use the superspace of n equal to 1.
Okay, but you can still use that. Okay, you use the superspace in n equal 1, but with the off-shell, with the auxiliary fields. You can still do that.
Yeah. Still, everything is off-shell. Okay, but you don't see explicitly the n equal to 4. What you would like is to have a superspace of where all this is part of the same superspace. You would like to write something maybe that contain the scalars of n equal to 4, which are 6, and all these till theta to the, these are 4 of them, theta to the 4, theta bar to the 4. You would like to have that, but this is not known. This is why I always use the notation n equal to 1. Okay? Therefore, this would be nice because if we would know that, I'm sure that the action would be even simpler than that. You will not have 3 terms, you will not have this. But
Do you know if it's not known or it's really
It's not
possible
known.
to build? Or is it really possible to build? I mean,
no,
there's
it's not.
some people-
There are several people that work on that.
Okay.
And for example, for n equal 2 is known. There is, for n equal 2, there is a formulation which you can put all this together in a big superfield. And for n equal 4 is known. But you don't lose too much because I say the only important, you can start from n equal to 1, write omega generic, and the import, if you impose that there is a symmetry between the change of the 4 fermions, this immediately say that this is the only possibility, this is the only possibility, and so on. Okay? Therefore, the n equal 1 description is completely. It's just that it's not manifestly n equal to 4. Okay? Okay, then what we did in the last.
And you have no hypers.
Sorry?
You have no hypers.
We will also do with hypers. I just
No,
say you
I
an
mean,
example.
I mean n equals 4. It's just the
No, yes, there is no symbol. Essentially, the idea is that every time you act with the fermion, with the supersymmetry, you raise the speed. Therefore, if you have a vector, if you have a scalar, you always can act with 0 to 1/2, 1. You will always have a vector in equal 4. This is why in n equal 4 there cannot exist a multiplet without a vector. Therefore, there is no. Okay, and then we evaluate the action of. We take a. We want to repeat this effective. Take the integral of these 5, all the fields of Yamis, of e to the action of Yamis. This was the starting point. And we say that this integral is an integral over the modular space of e to the minus. Is evaluated. Sorry. This was the sum over k, sum over all possible instanton sectors of integral over all the moduli of my instant, the action e to the action of the moduli. Okay. This is the object we would like to complete. Okay? And we notice that there is some special, very special moduli here. Always exist for any k. You will have always here a d4s, which means the position of the instant, and a d4 theta. Okay? We call it x0 theta 0, which gives the d2, sorry, this was only 2. Theta. There was this integral over all the rest of the moduli. This was just the A0. This was AM is the identity part of AM, while theta 0 alpha is the identity part. This matrix. Okay? For here we have all the other integrals, and here we have the action on the other moduli. And this action we see that was variation, was a delta function on the ADHM constraint. Sorry. ADHM. There was a delta in the fermionic ADHM constraint. And then you have this e to the S model mod that we compute over this model. Okay? Okay, and then what we said is that this is the superpotential, the effective W, effective superpotential generated by the instant. This will be function of my fields. For example, I will take this action where phi, let's evaluate it. This will, in general, this will be a function of the super fields. But just to compute it, I can just replace, since once I know this function, I can just simply replace phi and phi tilde by the superfield, and I will have my effective function. Therefore, what I need to compute is this function. By the way, we know from supersymmetry that this should be holomorphic. This is highly non-trivial, because we have seen that this action, S modular, was omega bar. Plus K bar plus the same with the theta. Phi bar theta over omega bar phi theta plus, sorry, the theta are exchanged. No, because this is, if this is anti-fundamental, this is also anti-fundamental. Okay? And then the K tilde phi bar tilde mu. Okay. Okay? This was the action of Jan-Mills evaluated at the instanton. Okay? And you see, highly non-trivial that this depends on phi and phi bar. But we know that this integral should be just function. It should be only function phi or phi. For the first check we can do in our answer is that the phi bar should cancel after we do the integral. Okay? If not, we will make mistakes. Okay? Okay, good. Any question?
When you say that you're getting effective action there, are you meaning that you, I don't know if this is important for what follows, but do you mean that you're integrating up to a certain cutoff, or you're?
No, I mean effective in the sense that is generated by instantons.
Okay.
Yeah. All this is exact for this particular terms. Okay. Then we will go. Okay, let's do this integral. I always make this summary wanted to stress what are the points that are important to remember. There are several details and technicals that it's not important that you keep in mind. What I remind in the summary is what I would like to keep. Okay, let's do the integral. Okay, now first let's notice. Okay, let's see what is the modulus. What I'm integrating here. Okay, what I'm integrating there. I am integrating, let's see, the bosonic moduli. What are the bosonic moduli? W, alpha dot. I will write all the indices just to remind you how big they are. I am integrating the bosonics is this, W, and you have A, M. Okay? And this was a matrix K by K. Okay? I am integrating now the Fermions, where mu, I, u, and you have also the matrix D, M, alpha. Okay, what else? That's all. Then we have delta lambda alpha dot. Okay, then we have delta DC, these are the ADHM constraints. Okay. Then we have a UK symmetry that we should know out somewhere. It's a problem. Okay. Then, what is the dimension of this? We want this action let's say a boson, the length dimension of a boson, let's say is 1, okay. And a fermion, mu or n is 1/2. No? Yes.
Could you please repeat why do we get on the contribution to the superpotential from this? From the instant, why do we get from the instant effective action only a contribution to the superpotential?
Because we have just here d2 theta.
All right.
You see, we don't have d2 theta bar.
All right.
If we would find here a zero mode, which is theta square or theta bar square, this would be a contribution to the carrier potential. Okay. The instanton are nice because they just give contribution to the super. It's very important. Okay, what I also want to say is that this cannot be correct. This cannot be the action. Because you see that these have dimension. Huh? So if I count here, how many? Okay, here I have 4 Kn. Okay, here I have 4 K squared. Here I have K times N, and this is complex 2 Kn. This is 2. This is Ij. This is 2K squared. Okay, this is minus 2. This is Ij. This is Ij. Minus 2K squared. And this is minus 3K squared. And this is an extra minus of K squared. Okay, this computation we have done several times here. No? But then we see. Sorry, I forgot. We have also this case. Okay, we have also Ki. We have also Ki. Okay, and they are K. Pki and K and B. Ki. Okay, I'm just writing the number of degrees of. Okay, what is the length of this? What is the what is the dimension of this? Is a meter square? What is that? I should just count the number of bosons, the dimension of this, the length of this is number of bosons minus fermion is 1/2. You see here. So let's see this. For example, let's say phi has dimension of energy. Phi is the depth of a field. Let's give this dimension of length to minus 1. Okay? If this is length to minus 1, length to the minus 2, W should have length to the 1. If this is length to the minus 1, omega, sorry, mu of K should have length to the 1/2. Okay? Therefore, the length dimension of this is number of bosons plus minus half number of. Okay? What is that? This is 4 Kn. This 4K squared cancels with minus 4K squared. Plus, yes, 4 Kn, that's all. Minus 1/2. Okay? here I have 2 Kn. Okay? And then here I have, okay, I didn't say how many multiplets. Here. How many fundamentals? In principle, you can have various fundamentals. Let's call F. Where F is going from 1 to the number of fundamentals. Okay? This is a QCD with several fundamentals. Okay? For each of them, you will have a K. Okay? For this is Kf. And you have K times Lf coming from here, and K times Lf coming from here. Okay? Therefore, this is the number of fermions is 2Kn coming from here, plus 2K Nf coming from there. Okay? What is this? This is K times 4n minus n is 3n minus n. Okay? Therefore, this measure here has dimension 3 n minus nf. Okay? Therefore, I should write here lambda. I should put here, in order to be 3-dimensionless, I should introduce a scale. Okay? That compensates for that. Because this should be dimensionless. Then I will introduce this scale to the k times 3n minus. Lambda has the dimension of 1 over the length. Okay? Therefore, you see, we start with a theory that does not have any scale. But the action, the effect created by the instant contains this scale. And we'll see what is the meaning of this term. Do you know what is this? Have you already studied the beta function in a quantum field? Okay, this is exactly the beta function. This just measures how round the coupling constant. Sorry. Sorry, another thing I forgot here is that this was the action, but this action will contain always, on top of this, we have always here a factor e to the 2 pi e to the a pi squared k over t squared. Remember, no? This factor is always there. This is just the contribution of the term f squared. Okay? Therefore, my effective action will be lambda to the, okay, I say this is the beta function of the Gauss. What is the beta function of the Gauss? What is the beta function? You essentially measure at one loop how runs the coupling constant. Essentially, what you want to do, if you have a gauge here, you have a gauge coupling, okay? Or let's say 1 over g squared. And you can see that if the gauge sphere is not conformal, this gauge will not be a constant. This will be some constant from where to start. And then there will be a logarithmic. This is J, this is. If you have a gauge series, what happens is that the gauge coupling will change, will be different at every scale. Okay? And you can compute this directly from a one loop computation and compute how much contribute every field to this log. Okay? This squared.
Sorry, if the theory is conformal, you would get just a
Beta will be 0.
Okay.
If the theory is conformal, we mean beta.
That's okay. But I was but you would just get rid of the scale, or you would not have instantons.
You will have 0 here. Yes. No, the instant is there. It's just that you need to
But they do contain a state, don't they? The instantons, like raw, etc.
What we'll say is that the coupling constant will not run.
Yeah, but you should not expect
The
to
instant
have
will be there.
scale in a CFT.
So
Yeah. I mean, where do you get the scale for the instanton size in a CFT?
But this is not the scale of the instantons.
Oh, that is not.
This is not, no, the scale is here of the instantons time. This is a generating scale. It's a dynamically generating scale. Nothing to do with the scale of the instant.
Which would break the conformally
Which will break. Okay, let me. Okay, what I'm saying is that if you compute, I mean, this is a computation. I suppose most of you have done. But okay, for supersymmetric theory, the formula, I will give you the formula for beta in general, is 3 times C of the adjoint minus sum over a representation C of beta. Where this C are some constant that depend on the representation. For example, C of the adjoint is n. This is just a group theory number index, and C of R, C of the phenomenon is 1. Okay, then you see, this is the general formula. This you get in any textbook. I mean, if you compute this one loop correction to the coupling. Okay, we are saying you have a coupling at 3 levels. How you compute this? No, you can have. This is the coupling at 3 levels. No, you have a quantum. You have at one loop. You will have something like that. Anything going around here will correct. This, if you compute this in quantum field, this will be logarithmically divergent, and then it will be proportional to some log. And this number depends on counts the number of particles going around the loop. And how much contribute every particle depends on the representation data. This is what they are. See, the vector module contributes 3C that job, and every representation contributes with this number CR, which is just the group series, the trace of 2 matrices. Okay, it's not important now. I suppose most of you know, but the important point is that you know that the beta function grows. And this is nice because you see, if I exponentiate that, if I exponentiate this, and let me put here a squared. Okay, if I take the exponential of this, a minus a squared over g squared k, this is exactly e to the a squared over g squared k times lambda with k, which is exactly what we are getting here. This is e to the k. This together with the e to the 2 pi squared, you could replace this was g0, was the coupling, was some constant. Now you can replace this by, you can either keep the lambda there, or simply think of this as a Hamiltonian constant. Okay, but it's nice already that without doing, you see, this computation, the beta function is, this has nothing to do with the computation of the beta function, but it's consistent with that. Okay, it's nice just from this counting you find that here you should put lambda to the k beta, which k beta is this particular. Okay, good. Let's go ahead. Then we conclude now that we have our effective function will be what? Will be the integral of d for x, the integral of d to theta. There will be some lambda a k beta. Okay? And then there should be some scalars, phi and phi bar. By the way, we know that phi bar cannot be. Therefore, there should be some phi and phi theta somewhere. Let's call phi the general scale. Okay? To which power? Again, just dimension analysis. This should be dimension 0. This is 4 minus 1. Theta is 1/2. 4 minus 1, 3. So this should be k beta minus 3. Okay. Okay, now very good. Okay, now let's see. You see that every now we should do this integrals, no? This integral over k theta and mu's.
Were we not integrating over theta naught x naught?
Sorry? This will be the effective function. At the end, this will be a superfield, let's say Q, so superfield in x and theta. Sorry, this was what you have in mind, that this was coming like this, and all this was coming from the integration of the model space. Okay. I just wanted to see what will be the final form. This function that we are looking for, the function that we are integrating, we already know how it should look like. It should be some powers of the scalar to the k theta minus. I was just giving you this idea. Okay, but then I want to also stress this point. You see, the integral that you are doing, the action that you have always one, combine always a zero mode of the fundamental with a zero mode of the joint. Okay? Then, in order that this integral, this Gaussian integral is zero, the two should be the same. Because every time I get down, I should take one from the fundamental and one from the joint. Except for these two extra we have. Okay? Therefore, the number of zero modes of the joint, Fermionic zero mode, minus the number of Fermionic zero mode from the fundamental should be 2. By the way, this is always true. All what I'm saying you can do in any n=1 theory, not precisely in this. This is a very important observation. The fact that this difference should be always true. But this is nice because now we know what is this. This was, the number of fundamental was 2kn. And the number of fermions in the fundamental was 2knf. Okay? Therefore, this means that k times n minus nf should be equal to 1. And this is very strong, because this is very hard to solve. Do you see any solution for that? You see, these are two integers.
K equal 1 and n equal nf.
K equal to 1
And n equal nf plus 1.
and n is nf. And this is the only solution. Therefore, we already, just from dimension analysis, we know that only k equal to 1. We simplify our problem to the simplest case that we could even write explicitly. Just dimensional analysis. And counting, sorry, not just dimensional analysis. We have all the ADHM construction here. But without the details, we know we just need the dimensions of the fields, counting, and just we are just ready. Okay. Therefore, now what we will do is just this combination. K equal to 1 and f is equal to 7. Okay, then the integral which I compute is exponential as effective w of 5 by tilde should be equal to lambda to the 3n minus nf. Okay? But nf is n minus 1. Therefore, this is just 2n plus 1. K is 1. Okay? The integral of dw, this is just 4. W's. You have 4A, but they are already here. Then I am not counting to do the omega. You have 4N, but they are already there. Sorry, you have 2N, so they are already there. So you have just T, 2N, U. Okay? And then you have D, N, K, D, N, K, theta. Okay? And then you have the deltas, which is just single. Delta of lambda alpha dot, delta of BC, also this is a single one, because the matrix now are K by 1 by 1. Okay? And then I have the reactions that I just cancelled, which was E minus single. The action I just cancelled was 5 bar omega bar 5 plus K K U bar 5 bar plus T. The same as okay? Let's write at least here the index. This is I. Sorry, I, there is no I, because it's K equal to 1. This is just U. And this is F. Okay? And phi is something that is in the fundamental, and you have as many phi as flavors. Oh, this is the integral that we want.
Sorry, can I ask you one more question about, like, I'm coming one step back about the beta function. Is it obvious that it's okay just to, that was the one loop beta function, is that correct?
Yes, in supersymmetric theory, the beta function gets only one loop correct.
So
this is a good point. In principle, in any case theory, you should, it's very hard to the beta function, you have one loop, 2 loops, 3 loops, and so on. Supersymmetric theory is only one loop correct. Okay. Okay, then we should do this integral. This is a Gaussian integral, this Fermions. But still, it's a bit complicated. Let's even simplify more. Let's take phi. You see, this phi have a flavor symmetry. You couldn't generalize using the flavor symmetry. Okay, then let's put phi in this way. Phi alpha, we will take plus phi S delta U F. Remember that F going to 1 to n minus 1 and U goes to 1 to n. This is a rectangular matrix. Okay? Therefore, phi n here is 0. You see, this is a rectangular matrix. What we are doing is we are putting something like this 0, 0, 0, 0. Here we take phi 1, phi 2, in phi n minus 1. Okay? And the same for phi tilde. For phi tilde, sorry, for phi bar. Phi bar I couldn't say. Okay. Okay, good. If I do that, you see what happened. The mu n, then here there will be 2 terms. One term when you do it sum over the flavors. S. Let me call S the sum from 1 to n minus 1. And then there will be the last one, is KF mu n. Oh, this is 0. The last one is 0 because I put distance. Therefore, this is 3 plus 2. Okay? Then you see mu n do not appear. Then the integral of mu n I should take from here. Otherwise I get 0. Therefore, These are two terms, therefore with this I can solve the integral of mu n and mu n. And all the others, this is a Gaussian integral. Okay? Therefore the integral of d4 d 2n minus 2, this 2n mu of this exponential to the, and the integral of k, dk, which is n. Okay? So you have mu, which is n, and then you have u bar, which is also n, and then you have dn kt, and then you have the exponential of sum from s equal to 1 to n minus 1 of km. This is delta, therefore this will be just ks, or kf, mu bar f, phi f, plus kf theta, mu bar, sorry, the other way around, mu f, this is a Gaussian. Okay? What this gives us? This gives us the product of f equal to 1 to n minus 1 of, sorry, this all this were phi bar. Yeah, it's phi bar. Then all this will be just the product of phi f. Phi f. It's a Gaussian, no? It's a Gaussian of a fermion. Every fermion, every integral will just bring two of them, and this will be the product of all. This will give the product of all phi f. This will give the product of phi f. Okay? What about this integral? Again, this is, since we put only non-trivial in this direction, this we can say this was u, now it's f, and this is phi f. This was UU, and this was, let's say, F prime, F prime. Okay? And the same for the D. And then the integral of fermion is the determinant in the denominator, for the Boston, for the integral of D 4n omega, or let's say d2 omega, d2n omega bar of exponential omega bar f wf omega bar prime equal to f prime. This is just again the Gaussian. This will be the product from n equals to 1 to n of 1 over the square root of that is if phi f bar phi f theta phi f bar. Okay, they are complex. This is the square root, they're very complex. This is phi. And you see that when you put these two together, the phi bar exactly cancels the two phi bar here. And you get the exactly product where we was double of phi theta was just lambda 2n plus 1 divided by product from f equal to 1 to n minus 1 of phi f. This is the phi f. And you see it has the right dimension, no? Because these have dimension 2n minus 2, the 2n cancel, and these have dimension 3. This is right. Then you see, this is very funny interaction, which you will never write in an action, the scalar field denominator. The instanton generate a prepotential, which grow when you take the scalar field very small. It's a very strange correction. Of course, this correction is small if lambda is small. If the gauge coupling is small, remember that lambda goes like e to the minus 1 by g squared. Therefore, this correction is very small. But if the gauge if the gauge coupling is not small, you will find NF is equal to n minus 1, or n is equal to nf plus 1. For some particular kind of series, you generate this potential, only for those series. And this will have this will change completely the way you actually behave. It's very okay. Let me just say that you can now ask yourself what is the here I just choose this particular choice, but there is a nice generalization of this, which you simply take. What you want here is something gauge invariant and flavor invariant that goes like NF. It should be NF times NF. Therefore, this could be a determinant of phi tilde fu phi u f. See, if this is diagonal, if this has this form, this is reduced to that. And this is the only object that you can write, which is gauge invariant, flavor invariant, and that when you put this will reduce. Therefore, again, you simplify the computation doing a particular case using the symmetry. You go to a particular choice, then you do the computation, you find a simpler result, and then you ask yourself what is the most general. Simple if that this is unique. And notice that this is, you could do even from the very beginning. You could even say, I will not do the computation. I already know that this should go like 1 over something of 2nf dimension, and the only thing invariant is that. And this is not, I mean, many computations have been done like this in literature. Many times you find the answer before doing the computation, just from the symmetries. It's very important. You always try to know where you should end. Okay, this finish with n equal to 1. Any questions?
I was just wondering again if you would quickly sketch the argument for having this one, for guessing this one. Yes.
This was KB. This was here you understand, no? You have lambda to the KB. This was coming from the fact that the dimension of the modulus space is non-trivial. Therefore, you should put this lambda in order to be to cancel. Okay? And this lambda is just k times this beta for me is 3a minus n.
Yes.
Now you want that this is dimensionless. Okay? In other words, what I'm just saying is now this integral here, the dimension of this integral, is the opposite of that. This is how we compute. How we compute this number. We compute simply what is the dimension of this. Then we already know the dimension of my integral. Okay? Then we already know this is the result of my integral, 1 over that. Therefore, we already know that this should be some field, the field have all dimension 1, 2, k beta minus. I mean, this should be dimensionless. This has dimension 4, x is dimension 1. You have 4x. This is 4. Theta have dimension 1 half.
So it's assuming that you only want to write it in terms of one field, this cube.
No, cube to me is every field.
Yes.
Sorry, yes. This can be everything. Phi theta, everything. Sorry. Like, what I mean by here is some arbitrary field to the k. This depends just on phi and phi theta. Phi and phi theta. The total number of phi and phi theta should be k theta minus.
So this is the unique. This is the only thing you can write which cancels.
Yes. Yeah. More precisely, if you now see the answer, this is exactly this. Because phi theta, you see, the only invariant that you can do is phi is in the fundamental, phi theta is in the fundamental. The only way to get the invariant is write phi theta. Therefore, you know that this depends just on phi or phi, and should come always in product phi theta. Therefore, they should be 5 by theta to the k beta minus 3 over 2. Still, I don't know how the index are contracted. Okay, and this is my computation saying me how the index are contracted. This is what is called the Mason matrix. Mason matrix. Which is gauge invariant. You see, it's a sum over U. Therefore, it's gauge invariant. It's a matrix in the flavor. It's source of flavor invariance because it's determinant.
Francisco, why did you cancel the bars there? I lost that part.
The fermions contribute only with 5 bars. And the boson contribute with the boson are coupled to both 5 and 5 bars. And come with the same powers. See, here I have product of F of NF, and here I have 1 over.
So they cancel with each other.
With each other,
With
yes.
each other.
They discuss between boson and fermion. Well, this is always what will happen. The only way you can get a prepotential which is holomorphic is that, in fact, this is a nice way. You can compute just the fermion. You know that the boson, whatever is the boson, is the same as the fermion, modulus squared down. Because they should cancel the 5 bars. From using the fact that you know that the result should be holomorphic, you can already guess from the integral of the fermion what it should be. There's only one hole, is that answer to the C. This is why it was important to me show that here you have the right zero modes to, you see, you have 2 extra zero modes, and I showed that here there are 2 extra. Then you should be sure that this is not zero. All what I'm saying here, you are sure that this is the answer, it's only if it's not zero. Either is this or it's zero. Then you should check just that you have the right number of the right counters. And this simplified out almost, this is called Affleck-Dine-Seiberg superpotential. This is a very famous computation. And there are several developments of this field.
Does such a contribution for the superpotential show confinement?
This is a more complicated question. This is not obvious. I mean, this is not. This is not obvious. Yes. No, you cannot conclude anything. No, you cannot conclude anything from this. But you can already start to see chiral symmetry break. For example, you can already start to see that this break. You see, break the U1 that. Let me we can discuss that. Already you can see very nice things out of very nice non-perturbative properties of N=1 just looking to this one. I mean, this is almost the only thing is known non-perturbative from N=1. Every computation you will see in the literature of N=1 is reduced to this. It's more complicated. You have a gauge theory which is more complicated and so on. And I should say, by my experience, almost all these potentials you can almost fix by symmetry. I have not found almost all of them just using the symmetries, the counting of zero modes. You count the zero modes to see that it's not zero. For example, as we did here, only if n is equal to a k is equal to 1. For example, this is important. Now you think, okay, maybe this was just for this case. This is true in any n=1 gauge theory with group UN, SON, SPN. Only k equal to 1 is true. Okay, and now we will go to n equal to 2, where the situation is opposite completely, because all instantons will contribute. Therefore, you cannot repeat this computation, because you can imagine this computation for k equal to 2 or 3 or 4. Then we should look for another way. What is the time?
It's 4.
4, okay, good.
Break.
Okay, before going to n equal to 2, maybe I can show you.
Should I?
Let me just propose you an exercise.
And then
The other side.
Okay, you say, okay, we have supersymmetry space-time. For example, we notice already that Q or delta what was sigma n dot is say sigma dot okay, we see already that supersymmetry relate, let's say, the field A, the gauge field, to the gauge. Okay? But we already said that this gauge field, we know how to write in terms of ADHM. Okay? Okay? Let me write this in this form. Let me call this quantity lambda. Okay? Therefore, supersymmetry relates the vector to the gauge. Okay? Lambda m is a particular linear combination of the gauge. Okay? But we know what is AM. Okay? What is AM? This was bar dm u. Okay, let's just write d. It's a form. D for me is the differential. Okay? Okay, but then this means that acting with this delta and this u, I should get, I know also lambda m is given in terms of the same ADHM data. But one was given in terms of delta, and the other was given in terms of m. This was lambda alpha dot. Therefore, what we can do, okay, let's say then lambda is equal to C alpha dot A M. Okay? Sigma M there was no nothing. M was a matrix. M was this matrix that was. What was this? Was lambda alpha dot J, and M was something that was lambda J. Okay. This is true. Okay. Then let's see if this is true. You see, we have a supersymmetry that relates space-time fields, but both are right. One, this A is written in terms of delta, the moduli of A are here, and the moduli of psi should be here. Therefore, if there is a symmetry between the two moduli should be related. Okay? Therefore, we can write a relation that says delta A, delta is equal to M. But M is for me this. Okay? This is supersymmetry. All the modules. let me remind here this mod. Okay? Then we would like to find what is how you realize this acting with this delta mod. Then let's do it here. Let's compute this delta moduli of U bar du. The trick is always the same. Every time I have delta U bar, I put here my U bar plus delta F delta bar. This is delta moduli. Du. Or if I act with the delta in the second side, is U bar. I act with the delta here, D of delta mod. Yeah? This was the first action. This was the second action, and then I put again here. This is always the trick. When you want to do ADHM, every time you have something acting on you, you don't know, but you know that U bar U is 1, therefore this term you can write like U bar with minus U bar delta U times U bar. Sorry, U bar du. U bar du, which is just A. Okay? So minus. This was this term. This term here, I can always bring here this U bar delta moduli of delta F U bar du. Okay, and here the same. Plus this guy. Yes, this maybe put this identity, let me put it here. This identity I can put wherever I want, no? It's just an identity. Then here I have U bar, D, and here again I can move delta, I can move here. Or I have 5 du delta mod U bar delta, is again with minus sign. And here the same. You can move here. This is plus U bar D of delta F, always minus, delta F, delta mod, delta bar, delta. Okay? I have numbers. Okay. Delta of the moduli, we say that was M. For every time I put 5 delta M, this is M bar. This is M. Okay. Now, this guy here, this is U. Okay, I get this term. This du, I can pass here again. Okay, V bar is changing the sign. Okay, and you see already we are getting part of the lambda. Lambda, you remember, was U bar M F T delta bar U. Let's look for the second part. Now, this D either act here, okay, and then I get again the second part, So here you see, this time I get minus u bar d delta f in bar. Sorry, here there was no delta. Okay, now I'm making a mess. Yeah, yes, here there was u. What I wanted to say is the computation again. You find that this together with that give lambda. This term, if you call this to alpha, let's call this quantity alpha. This is minus alpha a plus alpha a, and then you will see that you will get also from some of these, the guy will have the alpha. Let me see where it is. Okay, I should. No, please finish this exercise. It's not important for what I will. What I will do. What I just wanted to say is that you see that if you take delta is equal to delta mod plus, this is just a gauge. This is just a gauge transformation on A. Okay? Therefore, this is 3. Therefore, you get just that the delta mod acting on the AN give lambda up to a gauge transformation.
Sorry, but alpha A and minus alpha A plus alpha A cancel everything, right?
Sorry, no, this was the other side. It's commutator of alpha A plus d alpha. This is the gauge transformation. I mean, finish please. This is written explicitly. In any case, the important point is I just wanted to show you what is almost obvious, that there should be that the supersymmetry in space-time transform the supersymmetry in the model space. This is the crucial point. That the fact there is a supersymmetry transformation that relates the bosonic modulus to the Fermion. And for example, using this, you can prove that now you can understand now these two relations. This was the bosonic constraint. This was the Fermion. This is just the supersymmetry variation of that. You just take this, act with delta, with the delta here give m bar, with that here give. Therefore, you see, there is a supersymmetry also in the model space. For the moment, we have not used this symmetry. But what we will do now is exploit this, the supersymmetry in the model space. Okay. Sorry. Let me copy you here. If you're interested in this derivation, I will copy here all the steps up. Okay, the first thing, okay, this is, okay, the simplest way to show what I was doing there was the fact. Q of U okay, let's repeat this computation. Let's do it. It's just 2 bits. It's just this observation. As we did before, instead of acting on the whole stuff, let's just act piece by piece. Act on U. Delta mod of U is this. Okay? Now I can move here and move here. Okay? And then this is U bar. Sorry, when it was that, it was B. This is U. u bar, yes. Okay, this is u times this quantity, u bar delta mod of u minus, I pass here, delta f in bar u. Okay? Then, this quantity here I call alpha. And you see, this is just a gauge transformation. Therefore, I can pass here, I can say that delta of u, which is defined as delta mod u minus delta alpha of u, is just minus delta. Okay? This is a gauge transformation. You transforming the phenomenon. Now you do the same for u bar. And this is just the image. Okay? And then you do the whole stuff. Then this q. A is q u bar u plus, sorry, delta. A is delta u bar u plus u bar d delta. Okay, now use these two formulas. Okay, and then this is equal to minus. Now delta u bar was here, minus u bar. This was minus. Minus u bar n f delta du. And this guy is plus minus u bar d of delta u was this. Delta f n bar. Okay? Now this is what? This is minus u bar n f delta d u minus, now this d can act either here or can act here. Okay? Or can act here or can act here. Or these two will cancel. Ah, you see, if this would act here, you will have u bar delta, which is 0. Therefore, they cannot. Okay, that's all. This is it. And this is exactly that. If you compare with what the formula we wrote for lambda is. Then you see, it's okay, we got to complicate because we didn't write the, we didn't choose the right route. Okay, what time is? 4:20.
Can we have a break?
Ah, yes.
No, perché noi non vogliamo nessuno.
Sorry, no. I should finish half an hour. Okay. Okay, now let's start with n equal to 2. For now, the aim is always the same. We're going to compute. We have sum over k, q to the k. I call q e to the 2 by I tau. Well, now this is roughly e to the 8 e squared over g squared minus plus some theta, some pi. Okay? Q to the k. Sorry, and let me include also here lambda to the theta. This q, and we include also lambda. But then I will not no longer write lambda to the k beta here. It's inside. And then I have the integral over my modular space of my action. Okay. And we already know what will happen now is that we say that in this case, the matrix, you remember, there was this matrix whose identity part I identify with theta alpha 0. But now I am in n equal 2. Therefore, I have 2 of these matrices. Okay? Therefore, I have here a D4 theta. Okay? And then I have all the rest. And all this stuff I will call prepotential. And again, I will take my fields. You have a vector field. Vector field, you remember, contains a mu am. And a chiral. The vector field of n equal 2 is a vector plus a chiral. Fine. Okay, I'm going to get something. Okay. Then, okay, I say you that for n equal, I don't know if I want to introduce this or not. Okay, what I want to compute here is f as a function of this field, phi. I will take phi this constant, again, to some value. Phi is the matrix UV and UV. For this will be f.
Shouldn't be d square of theta? D to the 2 square, not d4. The integration is effective there.
I have 4 thetas. The 4 theta is what I mean.
Ah, it's a prepotential, sorry.
Sorry, it's prepotential.
Yeah.
Both is in n equal 2. Sorry, this was the narrow in n equal 1, this was d2 theta. So now I have n equal 2. In total, there are 8 thetas. They still chiral. Because you see, there are theta, not theta bar. This d4 is really d4 theta, not d4 theta bar. The chiral potential in n equal 2 will be theta theta bar. D4 theta bar.
Okay.
Okay, maybe it's a good point because sometimes I write in n equal 1 d4 theta. But in n equal 1, maybe it's not a good idea. It's better to write always d2 theta, d2 theta bar in n equal 1. All the formulas where I wrote d4 theta in n equal 1, it means d2 theta bar. Here is different. Here are 4 thetas coming from the chiral part. Instanton always gives just fermions of one chirality, not of the other. It's something you should always keep it. Therefore, what we want to compute is this integral. And we want to compute this integral. Unfortunately, all these numbers are different from 0 for any k. It's fk. But this is some over k, fk. And now all these numbers are different, all these functions are different from 0. Okay? Yes.
I can't understand this. We said that n equal 2 Supersymmetric needs is a special case of n equal 1.
Yes.
And in any n equal 1, Supersymmetric needs only k equal 1 contributes. So I would expect that only k equal 1 contributes in special case.
No. We say that the prepotential of n equal 1 for, yes, this is the means not only n equal n, because this is true if you don't have a joint matter. if you have adjoint fields, the theory is no longer n equal 1, it's n equal to 2, and this is not, okay, the statement is, it's true that only k equal to 1 contribute if you have just fundamental and anti-fundamental numbers. Okay? But not adjoint. The adjoint, then it's already n equal to 2, and you can see, essentially what, you remember this, our computation before. Our computation before was based on the fact, discounting of 0 modes. N equal 2 is, all these counting are very simple because the reason somebody point at some point, n equal to is non-canon. Therefore, it's less constrained by anomalies and things like that. For example, any n equal to 0 is anomaly because it's non-canon, while n equal 1, no. Okay, what I'm just saying is that forget about this statement that any n equal 1, 0, only k equal to 1. This is not true. Okay, good. And this is what we want to do. Okay, but then we should find a way to compute that. Then what we will do now is review this idea, which is called localization. It's a very simple idea, but very powerful. First, I will state this theory. It's a mathematical theory. Let's say the fact. Imagine you have a manifold, okay? And you have a U1 action in this manifold. Okay? You have some vector in this manifold. Okay? You have an action on the manifold. Okay? In such a way, if I give coordinates to this manifold itself, at the coordinate of my manifold, I have an action that says that by variation of xi is some function, psi of x. You can imagine, for example, rotation or a translation, or a translation, any action. Okay? But let's restrict to action of a particular kind, such a way that the number of fixed points, imagine that there is a point here that will not move. Okay? I call fixed point a point where psi I x is equal to 0. This means a point which is fixed. Imagine, for example, R2, the rotation around the origin. The origin is fixed. Okay? Therefore, imagine, let's just do R2. R2 is enough. This will be my action. Okay, theta is acting in this way, still delta c. And this is the fixed point. Okay. Then we will be interested in general in action where the fixed points, first point, is you have an action with isolate fixed points. With isolate, for example, rotation. Okay? This is the first. Second thing I need. You see, if I have an action of this type, I can construct something which I will call Q, theta, equivalent derivative, which is just the standard differential in the manifold, plus a contraction. What is a contraction? Contraction I define by simply saying a contraction of a form is just the variation. This is my definition. And for example, the contractions, if I have I theta t is minus, if I have I theta of dx1, dxi, dxk, this is this delta c is I dxj minus dxi This is the definition of contraction. Okay? I give you any form. You see, the contraction essentially is the opposite of the differential. The differential take a form, let's say a 2 form, and become a 3 form. The contraction take a 2 form and become a 1 form. If you imagine like the opposite, going in the opposite. Good. Then the theorem says that if you want to integrate, if you integrate a form that is close with respect to q psi, imagine that q psi is 0, then the integral of q, the integral of alpha, is just given by this simple form. Sum over the fixed point of the 0 form part of alpha dividing by the determinant of q squared. Okay, this looks abstract, but essentially what this is saying in this theory is the following. I mean, you are already very familiar with this. What you can think of Q. Essentially, this is saying that, you see, this is a sort of generalization of the standard, if you have a topological stuff, no? Essentially say this integral looks very complicated. But this integral is just the value is like the integral localized. You have the fixed point. You can think of this as a potential with several. The fixed points are like minimum of the potential. Then what this is saying that this integral, if you evaluate around the minimum, around each minimum, you take the value of the minimum plus the determinant coming from the small fluctuation around the minimum, the answer is exact. Just the determinant.
What is alpha? Is he a sum?
Alpha is the form.
Is he a sum of forms?
Yeah.
Sorry?
Is it homogeneous degree?
Is he
No, of
is
course
a
not.
sum of forms?
It's a sum of forms. Okay? Such that Q alpha is equal to 0.
So on what manifold are you integrating alpha on? If it's a sum of form of different degrees?
This pick up the top form. So the integral pick up always the top form.
Okay.
You remember?
So that's not really alpha. It's the top. Is the d-dimensional.
All the other interesting.
Alpha is a sum of forms,
Okay.
and this should be close. Okay. Notice the following things. You are integrating the top part, but the result is not coming from the top. It's coming from the low, so from the bottom. Therefore, it's saying, if you have a covariantly closed form, the integral of the top coming from the the nice things of this is, okay, so sorry, let me come back again here. What we are saying is that for some particular quantities, from some alpha that satisfy this relation, which is a very strong relation, if you integrate near the minimum, and this determines just the fluctuations, the quadratic fluctuations around the minimum, you get the cycle. So this is more or less what happened with the harmonic oscillator with the doubly kappa B approximation. You are making an approximation, you do the computation, and you find the exact spectrum. This is exactly here. You are making an approximation. Let's say, okay, let's go and first evaluate around the minimum. You do the computation, and this result you get is exact. And this for us is great, because it is exactly what we have. We want to have instanton, just evaluate around the instanton, just take quadratics on the terminal, and that's all. Okay? But we should find what is Q and what is alpha. But we know what is Q. We know something already that has this property, which is the supersymmetry charge. The supersymmetry charge, the supersymmetry charge is something that looks like this. Something, this square is 0. You have your moduli space. Okay? You can imagine the moduli space like M, and the supersymmetry like the differential. And this side will be the symmetries of the instanton moduli space. Therefore, what we will do is we will take the instant moduli space. Now this U1 will not be U1, it will be U1 to some power. It's the same thing. And we will compute this loop, that is the closed form, deform a bit. And this alpha will be the exponential of S. For us. Yeah.
Why do you just restrict to a U1 action?
No, this for simplicity. You can do now U1 to the R, but it's good that it's abelian, because any group, you can just restrict to the Kaplan, which is U1 to some power. Then once you understand U1, you understand U1 to the R, and for any group, this is enough, because you can always break symmetries to U1 to the R. Okay, now let's do the simplest computation you can do in localization. Let's compute the Gaussian integral. This is some integral you already know the answer, before we can check if this theorem is correct or not. Let's compute the integral of dx dy of e to the for you this is Gaussian, you know what is the answer of. But let's compute using localization. Okay. Then what is the U1 action? The rotation. For theta is x dy minus y dx. This is a U1 action on the R2. This is an R2, sorry. We have R2. This is a U1 action. We have only one fixed point, which is okay. Now it comes to the point that you were saying. I want alpha. I know already what is the top form, but I want to see how can I extend this to get therefore I want to now look for something that is e to the minus a x squared plus y squared plus something dx dy plus terms such a way that q d of alpha should be equal to minus IC of alpha. Therefore, I should now determine what are the dots such that d of alpha is minus d alpha inside. Okay?
And this is always unique.
Sorry?
Given the top form, the rest is always uniquely fixed by this.
Yes, you will see that. Yes, that's what you. Now, let's see, what is d alpha? D alpha is equal to minus, sorry, the alpha is 0. The alpha is 0. Let's see what is I psi of alpha. Sorry, the alpha is not 0. The alpha of this part is 0, but of this part will not be 0. Then let's see what is I psi of alpha, of e to the. Okay, this is. Let me write down. Is equal to, I replace dx by the component of dx here with minus y, for instance, minus y, sorry, this is the generator of the rotation. And then let's put, I don't know, some constant here. It's called epsilon. Okay. This is a rotation of epsilons. Therefore, this will be minus y epsilon. I replace the x, I replace by this component, minus epsilon, dy. And then minus, I replace dy by these components, x, epsilon. Okay? And this is epsilon d, this is minus epsilon d of x squared. Sorry, and there was always this exponential. Okay? Therefore, this is the differential of this is the dx dy is the differential of e to the minus a x squared plus y squared over a. Okay? So it's very simple. I just compute the variation of this and rewrite as a total term. Okay? Therefore, I can put this here. I can put here epsilon over a d of, sorry, epsilon over a exponential of minus a squared. Now you see that this d of that is 0. No? Now let's compute q psi of alpha. Q psi of alpha is d of this, which is 0, therefore will be I psi of this part which we already computed, is equal to that, plus epsilon over a d of this. Okay, but we already showed that I psi of that is minus epsilon over a d of that, for this. See, there is not too much surprise because in some sense, this is like the primitive of what I'm computing and okay. Okay, the important is that we will construct now what we want. And now we can just evaluate the formula, the fixed point formula, and say that the integral of e to the minus a x squared plus y squared dx dy is sorry, I forgot here. There is a factor minus 2 pi to the dimension, complex dimension of the manifold. Sorry, please correct this. The formula has this factor. Then this is minus 2 pi to the dimension, complex dimension of R2 is 1 times alpha, the zero form part, the zero form part is this, evaluate at the fixed point. The fixed point is 0, then it's just epsilon over a. Okay? Times the determinant. The determinant of this action, what do this action? This action says x and y 2 minus epsilon. This is just a matrix. Okay, the q is q. I j is derivative I epsilon j. Therefore, in this particular case, the only component non-trivial are q of is yx, which is epsilon, and xy, which is minus epsilon. For q is a matrix 0, epsilon, minus epsilon. Okay? Therefore, the determinant of q to the 1/2 is epsilon. So if you divide by epsilon, It's X minus. Ah, there was a minus somewhere.
Probably in the contraction you have, I mean, when you change the differential, the composite rule, you had a mistake there. You completed the contraction in the second row.
Here I contract. No?
Yeah, if that's correct, then the other is probably you had in the down formula. You had a minus instead, probably just.
Ah, this is plus because the differential. Sorry, differential of A give a minus already. Then this was plus, for here was minus, and now you get. And this is, you see, epsilon cancel, this is a miracle. Everything seems to depend on epsilon, and then we get the answer, 2 pi. This is the Gaussian integration. You see, we introduce this Fourier parameter epsilon. Every step of the computation looks to depend on epsilon. The final result will not depend on this epsilon. All this was an artifact to construct an integral. Okay, now this is a very simple integral, very stupid, but you can imagine that we will do now for our model space. Okay, then I will stop here, and it's okay. Okay, I stop here, and then the next lecture, which is the last one, we will finish this, we will compute this prepotential in general for n equal to, or maybe make an example, a simple example. And then I will devote half an hour to the idea of the Seiberg-Witten curve.